Hello class, this is section 5.5 and in this video we are going to talk about the self-adjointness of the Sturm-Liouville operator. Now, self-adjointness is actually a really important concept in mathematics and we are just going to see a tiny sliver of that in this class. In full generality, what self-adjointness is as follows. We consider a multiplication between some u and v. This can be several kinds of multiplication. And we say that an operator L is self-adjoint if the multiplication works the same if you apply the operator to the first term and if you apply the operator to the second term. So it makes no difference which term you apply the operator to. For instance, if star is just a regular multiplication by a constant, if L is the multiplication by a constant, that operator is self-adjoint. So let's consider the Sturm-Liouville operator. And we're going to define our multiplication star. In this context, our multiplication is going to be integral to a to b u x vx dx. So multiplication is just regular multiplication, but including an integration from a to b. So in our context, when we say that the Sturm-Liouville operator is self-adjoint, it means that we are saying that Lu times v minus Lv times u is 0, but this is the same thing as integral from a to b of u Lv minus v Lu dx equals to 0. Now you may remember this formula, called Green's formula, which we discussed in a previous video. And it goes like this. And remember that p, u, and v are all functions of x. So a Sturm-Liouville operator is going to be self-adjoint when Green's formula just gives you 0. So this p u dv dx minus v du dx term must also be 0. So remember what we're doing is that we're just plugging in the boundary values. So this is the equivalent to saying that pb u b d vb dx minus vb dub dx minus pa ua dva dx minus va dua dx equals 0. Now this seems to be a very complicated condition, but luckily we have some other information. Remember that our Sturm-Liouville problem came with some boundary conditions, and we said that a Sturm-Liouville problem was regular if it obeyed some properties, and among them that its boundary conditions could be written in this form: beta 1 f prime plus beta 2 f, beta 3 f prime plus beta 4 f for the two ends, where beta 1, 2, 3, and 4 are all real numbers. And we're going to claim here that if u and v obey the same boundary conditions, the same regular boundary conditions rather, then L is going to be self-adjoint. In other words, that we have this nasty property and nasty equation here being equal to 0. It actually isn't that difficult to check. So first of all, notice this term here. We have u b v prime b minus vb times u prime b. However, we know that both u and v obey the regular boundary conditions, and this implies that v prime of b is equal to minus beta 4 VB over beta 3. And this comes from the second boundary condition over here. If we solve for f prime, remember that f is set equal to v at this point. And similarly, of course, we have u prime b equals minus beta 4 over beta 3 ub. They obey the same boundary conditions, so the beta 4 and beta 3 for both u and b are the same. Well, if we substitute that in, we're left with ub minus beta 4 over beta 3 times vb minus vb times minus beta 4 over beta 3 ub. And these are, of course, the two same things. We get 0. And similarly, if we do the same trick for a, we get that this first term is equal to 0, and the second term is also equal to 0, and it doesn't matter at all what p is. And we have our condition set equal to 0, and therefore our Sturm-Liouville operator is self-adjoint. And this means that as long as our UV obey the same set of boundary conditions, the L is always going to be self-adjoint, but that's going to be fine, because remember, we're always going to apply the Sturm-Liouville operator on eigenfunctions. U and V are always going to be eigenfunctions in our context, and these eigenfunctions have to obey the same boundary conditions.